All right. Thanks everybody for coming tonight. So this is Knox3dp. So we've been kind of brief interlude over the summer, but you may have been here or with our group last month. We had Local Motors present with Knox data. That was a really cool presentation. If you missed that, we actually streamed it. We actually streamed it live on our YouTube channel at with Knox Devs, which is kind of an umbrella group for all the software development community in Knoxville. And so Knox3dp, we're kind of like kind of underneath an umbrella, although we're kind of on the edge of that. So what's really cool is Knox Devs provides kind of an umbrella for all of our groups. And so with that, we also have a Slack channel that Knox Devs provides, which is really cool and how it got started. So Knox Devs got started about 2 years ago with a couple guys after a conference here in Knoxville, and they realized, wow, there's all this great kind of tech and knowledge base here in Knoxville, but no one communicates. We didn't know that, any of us. So what's cool is from those 5 that started it, there's now like 750 people in Knoxville that are on this channel, and it's really, really great. So if you you can sign up for it. If you go to knoxdevs.com, right here you can join us on Slack. And so yeah, so now we're actually up to 800. So I have you there, but it's really cool. They have a lot of different meetups. So you go to the meetups tab, you can kind of see all the ones that are underneath. And so a lot of them are a lot more on the software development side, but there's all kinds of stuff there, and obviously we're there too, which is really neat. So on the Slack, and why it's cool, why you should do it, we actually have a 3D printing channel. We haven't really got a chance to really use it a lot, but I'm really hoping we can use this as a place to kind of take conversations offline. So in between these meetups, things you're working on here, this can be a place for it. If you're a member of Knox Makers, there's also a really more vibrant 3D printing kind of channel they have there on their Mattermost, which is a very similar platform in Slack. So both of those hopefully are good resources to kind of carry on some conversations we have and we have tonight outside. So anyway, so what I posted on there is we posted like really cool build videos and all kinds of stuff related to that, as well as when these meetups are. So that's an option for everyone. And finally, if you go to our website, I have a little bit of stuff here. I'm going to try to do a little better about putting more things on here. But if you know somebody who's interested in this kind of space, we're trying to still build it and develop it and get more people out. So if you know somebody that would be interested, send them this link, knox3dp.org. In there, I have a little bit of description of kind of what the group's about and some of the topics there. And then I have links to our meetup and how you can join on Knox Devs, like we just talked about. So one thing that's really cool about it is that we're supported by Autodesk. So Autodesk makes a product called Fusion 360, and we'll have some talks in the future on how to use that product. And so what's really nice is that they help support us with pizza and some of that, so that's great. Yeah, it's really exciting. What's really cool though is they let us run the meetup how we want to, which is really nice. So, so in the past we've talked about open source software, alternatives to CAD stuff. We also featured some like how-tos with Fusion 360, which is free to download and use. So we'll have some more stuff in the future on that. And I'm always looking for input on talks or things you want to know or learn about, whether it's CAD or 3D printing. That's kind of what I hope this space is for us. So anyway, so without further ado, tonight, while you're all here, talk a little bit about how you get more out of print builds. So, so Bruce is going to talk a little bit, kind of some tips and tricks, some things he's kind of worked through, as well as why things fail. Maybe sometimes why. Maybe they still unknown. But those kind of things related to that and how you can use that right now, whether you're printing on Bumblebee or you're printing on a desktop printer that you may have access to. So we'll walk through that. So Bruce, you want to talk a little bit about yourself?
Do a little show and tell.
Yeah, absolutely.
So, how many people here have printed? Okay. How many of you have your own printer? Okay. How many of you hate your printer? Okay. So, I've never met anyone who says, I love this thing. Kind of, usually at first, and then after a little while, things start going very, very wrong, unexpected, confusing, and you think, oh, I'll replace a part or two, and it still doesn't work. Right? So it's all about materials. Where you want to go. So I'm going to guess most of you have what's known as a fused deposition modeling printer. So anyone have lithography, powder bed, any of those others? Okay, good. Because I've trained everything tonight for FP. So. Okay, so I've been in printing since the late 90s. So big powder beds, big machines, all that. And over time, I have tried to isolate all of the problems that can come along. So at the end of tonight, what I'm hoping you'll have are the 4 things you need to remember above everything else. And I'll explain to you what this is. Moisture, 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 and sandpaper. Sounds absolutely crazy. So I've been building these printers. This is probably about 18 years old. Back we were trying to measure how much force it needed. We built custom printers with ceramics and custom components and water cooling to isolate and identify all the boundaries. There's your print if you like it. So we can nail every single parameter down and find out what's really going on. So, how many in here want to do more than just print plastic, PLA, ABS, nylon? You like some metal? Ah, there we go. There's always someone who wants to do metal with a printer. Okay. Who wants to do a small business and transition out of your printer into, say, your pre-production run of 1,000 parts or so? There's that guy. So you can do this quite easily. So there's one, and tag of tricks on here. So how many people here use glass for their beds? I'm sorry. They produce beautiful, beautiful textures, smooth. However, there's a little problem with glass. It's flat. So regardless of your chemistry, regardless of what you're doing, regardless of your hairspray that you've smelled like many a time, many nights trying to get away from it, despite all the times you've ran into it, bumped into it, and otherwise, you can only be as good as the surface area you're gripping with, period. So, how do you make your part bigger and keep it the same size? I like this kid right here. I want to see his expression. We're going to do this to the surface. There's a lot more to grip. And you'll have to rework that surface. It doesn't matter if you're using Captain. Anyone use this stuff before? Okay. Great for ABS. If you ever do use it, there's a ton of it here if anyone wants any. You can have a whole roll if you want. A little bit of water, and you can position it, and then it evaporates, and you're good to go. That's the trick. So, some people try it and they learn to hate it quickly. But even if you use tape or some other film, rough up the surface. You'll be surprised. You can get 4 to 10 times the surface volume that you can't get with that flat glass surface. Plus, the glass doesn't really bond to the plastic. It kind of lifts off, makes a little vacuum. As you print over time, as you print parts that are taller or too large, based on the environment. It's not about the environment. It just lifts up enough to get air, and then the piece just keeps peeling up. How many people have peeled? Okay, there you go. So, when you're doing sandpaper, I don't care what material you use, I'm a big fan of Garolite. The Garolite boards, they're wonderfully simple and inexpensive. I'll leave it showing you. I'll just stuff around. I think about, I always drill holes and put magnets on my board so I can slide it off, put it on, and slide it on. This is actually from the kitchen. That's what you get. That's what you're looking for. Now, I'll let Joe start passing the picture there.
What about the board solid glass?
It's really great. It's really smooth. You can actually sand the boards of the glass. Problem is, when you sand it, it makes microfractures. And when you heat it up, sometimes trying to take your part off, well, you got to do it. Okay.
So the word that you use for that flat, that flat piece was somehow use the word. What's it called?
Garolite or FR4. McMaster should be your best buddy. If you don't know McMaster, you don't.
400,000 items.
Yeah, it is close enough. I believe in English, so if I misspell it, it's intentional. The Garolite is really great, and it'll take you up to where you've got parts in length to a whopping 75 millimeters, 7.5 centimeters. Isn't that really fantastic? No, it's not. It sucks. Everyone wants, usually on these printers, you're printing parts between 100 and 140 to 200 millimeters. And as soon as you cross this magic line, somewhere between 75 and 100, it goes from, oh, I can print that, to it's 4 days later. You've just made new words to cuss at the machine, and it's still not doing it. And there's simple reasons why. So, some of my favorites that I've seen people use is Garolite, Captain Tape, glass, hairspray, blue painter's tape. A lot of blue painter's tape, I've seen that used a lot. But you know what I really hate is that you're going to use it, and now you've got to peel it, scrape it, do this stuff, right? So the reason I like the Garolite for nylon, PLA, and ABS, it's a universal surface. Okay? It does a lot. If you can heat the board up hot enough, usually about 120 C, then you can get it hot enough and it'll bond. And what happens is when you cool it down, it shrinks at a different rate than your plastic, and the piece just pops off. It's quite beautiful. Holds it down, you print the part, you're done, you walk away. And there it is. So, who prints nylon? Anybody print nylon? You will want nylon. You got to be behind you. You will want nylon. You have to use Garolite for nylon. Prints beautifully, bonds to it. So, I'll start looking at some craziness. Take this strong young man right here. Which that doesn't. Yeah, it's wrong. It's good. Why?
Well, it might just be like the surface it was on. It might have like been it somewhere.
Possible. Can you spot it by eyesight? Oh no, it's a quiz. You weren't expecting that. Okay. Try breaking it.
I can't break it.
Okay. What you got behind you? Let me break it. So, not breaking. Okay. Let's try something smaller. That weighs about 10 grams. Break it. Go for it. Come on, it's 10 grams. Feel free to break it. It's a strap bar. I'm not taking you up on breaking. You're a strong guy. Everyone wants to break stuff. It's usually not. try a bigger guy. Now try making that. You would tell me why this is a bad part. Try breaking it. So, what I focus on isn't art. I focus on parts. To be parts, you have to be accurate. Perfect. Now look at the inside. What do you see? White.
It's white.
Do you see the holes in it?
Yeah.
Okay. Does it look like this guy?
Yeah.
Okay. So, what we're dealing with is the temperature is too low, and the setting is wrong to not put enough material. This guy has a print exactly the same issue. Take a look at that. We'll pass these around. Go to the bottom, good one. Good one at the top.
Gotta give it some time. There's the jar as well.
Yeah, so you didn't know you was going to come here and break stuff. That's kind of fun. I love breaking stuff because that's when you learn.
What is this material?
This is ABS.
ABS.
The simple old ABS. I print in black usually when I'm doing test runs or just test components over time. Because when you break it, it makes a nice pretty white. The more white, the better the bond you have. It's a simple measurement. Plus, you put it under a microscope or a magnifying glass, you can look for little grooves. This is everything in your print if you want a mechanical part. And the reason is, most people print, they got it to print, the last thing they want to do is break it. Sorry, some of us might break these stuff. So, here's one you'll like. This is one of my kids making them wheels for little robots. Okay? One of these wheels is smooth. That one's not. This is thermal process thing. TPU, something rubber, so it's soft and spongy. Bend it, break it. Take a look at that guy. Take a look at that guy. See if you notice the difference.
I'm sorry, but these all look much better than my ABS.
That's what I'm thinking.
Do what?
They all look better than my ABS.
Well, that's what I heard here.
Do you have an enclosure?
So,
That's a trick question.
that's a trick question. So, it takes time to identify problems. Everyone's seen this monstrosity, right? How many of you have seen print jobs this bad? Not good. Well,
I've seen someone else.
here's another. Break that one. It's a fraction of the size of that one. Get you used to how you identify the problems. Uh-oh, that one's really small. Now I'm going to ask Joe for one, and then pass it around. So on this, what's wrong with that print? We'll make him grab his glasses out.
Oh, yeah, well, the surface isn't complete.
So let's start identifying problems. All right? Let's start identifying problems right off the bat with some of these parts. So you guys think are nice and I think are terrible.
Yeah, this one really sucks. I mean, there's inconsistencies on the surface. There's inconsistencies on the surface, but I have no idea.
Okay, perfect. That's an honest answer, and we love honesty, right? Because nature doesn't care if we don't like it. So, when you think of the print heads, the heaters, some are longer than others, some are much shorter. Okay? Some have drivers that run off, like Bowden extruders and otherwise, they run way off. So, what's going on with some of these prints? Let's take the one Joe just had. It's got grooves in it. Grooves occasionally, they go, they stop. Right? They're starting, they're stopping. Some you have. So, what could be going wrong? Under extruding. So you can have, so there's a ratio that your software is using that the motor drives to drive that filament down, and it could be too low. They try to make it this universal number that they're trying to play with. You kind of adjust for each roll. 85 is stabilized, manufacturer providing it. So here's the problem. I could be any of these and produce the same results. Depends on the printer. If you have a printer with a longer extruder, you usually have most of you, have you taken your print heads off? Look at them probably as you were cussing. Don't worry, you will someday, but it's okay, it's a 3D printer. So what you can do is, you're gonna find this little white tube in here. And it looks good. Most of those problems you're looking at came from the little white Teflon tube running down into the head.
Guide to
The little filament guide tube. So, one of these I'm going to pull out in particular, and some of these I'm going to leave isolated because they look really horrific, some of these. Okay? That one looks pristine. It's completely bad. And you won't know it. It'll run, it'll print, sometimes it'll stop. How can you tell this little guy? Because it'll cause your gaps, it'll cause your layers not to bond, because you've got one number that you're expecting it to do a solid fill of the part, and it intermittently gives you half the volume. So, what you do is take a look at these, and then take your finger and slide over the little ridge there. Here on this one. And I'll explain what it is. So, there's those horrific things, and then fingernail on that. I'll draw you a picture of what's going on with this. It comes down to a big chunk of your problems printing, even sticking to your table, is how low it's flowing. So how much pressure is inside that head? A lot. So you have this, which is down to, you have your head, heating element stuck in here, you have a nozzle. So up here you have your driver pushing that filament down with quite a bit of force. It's a very small diameter, it puts a lot of force down. By the time you hit down in here, and you're trying to lay down this down tube, it has, as it transitions, if you look at those heads, you'll find all the bottoms look horrible. Because it's transition in temperature. Now this Teflon, I'll tell you, it's good to 700 and some degrees. Yay! No, it's not. All plastic morphs and bends. Like, plastic has half-lives. It'll change over time, very short periods of time for some. Teflon in particular doesn't like too much heat over time and pressure. It's its nemesis. So the little gaps between your head and your other under pressure and under temperature, especially if you don't know that your head's breaking 240. Most people don't calibrate their heads on their extruders, just assume the machine's right. It's usually wrong, 5 or 10 degrees. You go over 245 degrees, and you're on a timer for how long that little piece will take until that pressure causes it to buckle. And it doesn't just buckle, it actually, this inside will narrow ever so slightly. And that's the transition zone from the glass state. Plastic doesn't melt, it just gets glassy. Okay? Glass transition, thank you. And so what happens is that builds up that pressure because the temperature is off. Teflon gives it, instead of, you'd think it would just push out, it's pushed down because of the friction of all this. And it buckles and it curls up on the inside. Now, you go to clean out your nozzle because you think, nozzle's clogged again. It's not clogged, half the time. Now, if you're in a room full of dust, maybe. But most of these nozzles are 300 to 400 micron large. That's huge in this scale. Dust is 10 micron. So unless it's burning or otherwise. Things to look for is black marks on the tube, black marks in the threads. Sometimes you're overrunning heat. This Teflon is popping out. And then now your straight line is kind of like this, right at your transition zone. You heat it up, it works for a little while, you extrude material. Sometimes you get the sputter. And then it starts running smooth, and you think, I got it. Right? Sound familiar to anybody? Then it stops mid-print. You just wasted 2 hours. You come in there, you see disaster. So believe it or not, that down tube is a horrific thing. So some people say, go all metal, all the way down. And that's what I prefer, but there's a problem. Some of these machines do not work well with all metal because why do we want the Teflon in the beginning? It's slippery. Yeah, you put more pressure, it adds friction. So if you switch to metal, depending on how you're printing, you end up with more pressure. Now your motor, most of these motors are running. And the manufacturer makes these motors, they're picking the cheapest motor they can to do the job. So they get a 30% leeway. You change the angle of the nozzle 5 degrees, you can exceed your pressure on the printhead. The flatter the inside, the more internal pressure goes up, the more of these fail, your motor starts skipping. You won't even drive it through. You're like sitting there looking at it, wondering why it won't even drive through. So that's something that'll happen with the metal, unless. So here is a Bowden extruder. Who knows what Bowden is or has one? It's where you got a driver. There's direct drive or Bowden? Okay. Anyone with Bowden? Okay, good. Gosh, I hate those. Well, I hate those because they start out really great, but the problem is that it's spongy. So they push down unless you get it exactly right, it oozes, it drips, it keeps making strings everywhere. Direct drive's the way to go. Is yours direct drive?
I don't really know.
What kind of printer?
The one with Chris left for me.
Okay. Is the motor right there on the head?
Yeah.
Then it's direct drive. So number one is that little Teflon tube that you're going to. So, anyone had a printer more than a year? Good. You ever print in the winter versus summer? Okay. So there's a few things. Your head temperature. Your bed temperature. What's the temperature of your filament? And what's the temperature of your environment? Change any of these 5 to 10 degrees and your printer will not be the printer you've come to love and the printer you hate. Now you try to mitigate this by putting boxes around it to keep air flowing. That keeps the irregularities. But little trick, most of these enclosures with the motors on the inside, you can heat up to roughly around 45°C without damaging anything, which means that the incoming filament is okay at 45°C. At 55°C, ingoing between the motor heat and the buildup of the motor itself, it'll transition into your nozzle. How many of you have gotten this nice little guy where he just sort of clogs up and wraps around him? Your motor's too hot. Is it the open box or is it minus? The motor sometimes will get so hot. Have you changed fans since you bought the unit? Have you changed fans on the unit? Was it an exact match fan?
No, it was just, I actually stole it up.
So, what happens is you're off by about 5 degrees, and that's the glass transition from the heat coming up from that tube. And it'll just keep coiling around. You may get it to run. If you plot the day and its temperature, and the temperature of your house and the humidity for your environment, you can watch it print or not print. And I've actually done tests on this just to see why something wouldn't. That's kind of crazy. I know that's just. So that's important. It's the temperature of your filament. You don't want to get any hotter than 45°C entering into that print head. You keep your fans running. Get it cool. Water cool it. I've water cooled many a print head. It's a hassle. It works. Awesome. There's reasons for that. Yeah. Water cool the print head. Well, you want this part to be hot. You don't want anything above that to be hot. So you run into this nice little balance that everyone's trying to get when they deal with these printers. I'll come back to the bed in a minute. The material that you like. Who prints ABS again? You. Anyone want mechanical parts? Usable mechanical parts, right? Okay, no problem. So, you have a glass transition point. There's a certain amount of distance between that and the fine point of the nozzle. The depth of your head defines, the depth of your nozzle defines how fast that transition occurs. And then you have your environmental to push into the actual nozzle. Okay? Here's the problem. Years ago, everyone was using 3mm filament. You saw it everywhere. They were awful. The reason is that you had to have more time for it to heat up. So if I take something this big, the heat has to work its way into the center and up from the center of the nozzle, trying to do this. The larger the filament, the slower it can heat. As you go with a smaller filament, and I've actually ran filament down to 65 micron, and it's a whole new world. I wish I could buy it in bulk. I'm running everything that way. But you have to make it, so it's really awful. But you have almost no head pressure and otherwise, and you're heating. So if it takes a shorter time to heat, you can make that smaller, which is what all these new print heads do, much smaller. The nozzle transition is less. You can go from cold to hot. So when you're sitting there idle not printing, you have less material heating constantly oozing out the tip. The old 3mm ooze all the way down. They just run forever. And that also means your print speeds are faster. Because when you retract, you need to measure where this transition line is. That's how before you retract to up here. These materials sitting here. But that would give you the cleanest transition. You will get rid of all your little stray little lines. You'll get rid of all that. Okay? So the shorter you can make this, the better. Now, if you water cool everything up here, or put some heat sinks, get this as cold as possible. The colder you get for this driver, the more exotic materials you can push. If you take a flexible filament and you try to run through and your machine is running too hot, bad things happen. You'll spend forever digging that out, wondering why you just broke. So all these. So when you're using the softer materials, the more problem you're going to have trying to maintain that print. So how do you get your build environment to 45C if you're printing ABS? PLA, you don't care, right? You're just worried about lifting off the glass. With airlight and sanded surface, you print almost anything you need. Up to ABS and nylon parts from 75 to 200 millimeters. That box, if you go up to 45C, you can't go all the way because your motors. You can print up to that size and that won't work. That is your ABS best print. The PEI alone is not enough. PEI unsanded, without a texture, is just as bad as any other board. Get your PEI above 110, and it's permanent. You will break it long before you get that part. So it's a scrap. So
release though with cool down.
PEI will release with encouragement. You're better off to not bond it, try to bond it to a metal board or bond it onto your table. Maybe some little metal clips. My what I do is I cheat anytime I got one of these boards and I want clips and I'm losing my clips all the time. What I do is I just make a real quick little metal clip like that out of piano wire. Clips right on the board so it doesn't get in the way of my printing. You have to go over the PC board if you're using a PC board here or over other mechanics underneath. All that PEI always has a natural curve to it. So you want to put it on there where it curves this way. The temperature keeps trying to curve it up higher. You put your clips on the edges, and this one in the middle. And guess what? You can use it. And then let's say that a lot of people have your handy dandy extension, right? If you've not bought one of these, buy it. There's no reason not to have one of these. You slide it up underneath your board, pop it loose. For PEI, it's especially good because the PEI, if you have to take your clips off, flexes. You flex it, the little edge, off it comes. You put it back on your board, put your clips, fill with some alcohol, and print again. And you don't wait. You just keep running and running and running. So, in a lot of prototypes over the years, a few thousand. What I like is when you can print something, there's no screws, there's no components. I keep adjusting my parameters to a certain set. 45 sequence ABS, 120 degree print bed, PEI if it's anything larger than 100 millimeters. Up to 200 millimeters. That will not help you a lot. What I like is when you go to assemble something, you get that little SAS line. And you can stop using screws. Because unless you apply the force, torque in the right spot, reusable, etc. So you get your parameters right, you get your heat right, you get your surface, live with this stuff. This is, I think it's 60. You're right. Yeah, I want the most texture on that surface. If I can get 10 times the surface area, I can go 10 times bigger one. So I take PEI. What I want to do is I want to go in and load the machine. I'm going to say go and walk away immediately after I do go. So I've got all my machines on my printer set up, but that's what I do. I don't even think twice. I just come back when it sends me a text saying, hey, I'm done, and I go check it. So let's pause there for a second. We'll start talking about some of the other more fine details. Is all that kind of making sense? How to identify your bad tubes when you don't know what's going wrong. Check the temperature with an external measurement, whether it's a thermometer, whether it's an infrared gun, a little piece of black tape, let it burn, that's fine. Permanent marker is enough to pick up the temperature. So a little permanent marker on your head and a little long contact, you get pretty good temperature. The way the electronics work, they put in resistors. It could be off 10%, 10%, 10 degrees or more. You think you're running 230, you could be running 245. You could be running 225. All places tell you just keep upping it. Just up the temperature. Then you're over temperature. Tube, fan, you replace the nozzle, you fix everything, you think it's clogged, you repeat the process over. So let's see. What's other problems? Is there any problem I'm not mentioning people have had? He has one. Go. Inconsistent overnight. Buy good or better. I am a stickler for buying from particular vendors. So I thought this might come up. So I've got a trick. So I have a little spreadsheet, and what I do is I get new filament in, and I measure it 5 feet, or foot at a time for 5 feet. And what I measure is, just take my caliper, I don't really care. I measure this way, and I measure this way. I plug in my little spreadsheet, it gives me the actual surface area. And it doesn't matter if it's off when I measure it, it gives me an average. I do that over 5 feet. I'm as close as I'm going to get on that foot. You'd be surprised how much that'll make up for. You may have a print with a small section that's not looking right occasionally. That's a usable part. Okay. Does that make sense? Okay. What other one?
Auto versus manual method. What do you use? How do you do it?
So, are you talking about for your leveling or what? Which is
This one I was there.
I'll let you go. So,
And just going on that some more, since you said use removable PEI, how frequently do you have to recalibrate, I guess, for that?
this is going to sound strange, but I recalibrate maybe once every month and a half. Yeah, I know.
Running the same temperatures?
Oh, no, running different. Yeah. So what I do is I cheat. The first thing I do is when I'm calibrating the machine, I bring it up to temp, and I don't. If I'm doing a manual, like on one machine, I don't know what's on it. Always calibrate it at temperature, even if you have to throw away whatever guide they gave you, right? And the reason is that metal expands and it moves. And I replace a lot of these have a spring underneath. You guys have a spring underneath the bed. Okay. I replace it with heavy springs. So I really crank it down, and then I bought springs that were stainless steel. Stainless steel hates to conduct heat over time, so it's less of a problem. And also the higher torque lets me lock it in, and it has lower expansion rate. So if I'm off 5 or 10 to 20 degrees from the material, like I'll run like 120 if it's PLA or ABS, I'll still run about 90 for PLA. All that stuff for me. And that is just to keep this bed from having to move and have to go in there and mess with it. On that machine. A big machine, yeah, it's got an automatic piece, and it goes over and it scans the whole table, takes samples, adjusts it, but then that guy's running an 18-pound bed on my big machine. So that's when we get into what happens if you're going to go larger than 200 millimeters. We'll talk about that next. That's a nightmare. So, does that kind of make sense? Stainless steel, some good washers.
So you're ignoring your hot end growth down into the bed?
I kind of set my hot ends, and then I measure it all at the same time if it's a manual setup. My kid's machine, they use the manual setup, so I get this set up once, and I change it. I go in there, we go in there once a month and a half or so, and we'll recalibrate it just for a quick measure. Crank it down. The nozzle was kept very short, so I modified the machine a little. So I reduced the length of their down tube. I moved it closer. I beefed up the fans so that I'd have a higher temperature differential for them. Beefier fans, big old monster roaring things. Redirect all the air out the sides and up. And then by shrinking that top piece and limiting their temperatures, it's just foolproof. I can print, we print all the time, snap together parts, Legos, all kinds of stuff. So that's one. So the big machine is a little different story. ABS was originally made to shrink and deform through thermal use. They wanted it when they printed a mold, machined a mold, and you got that part it's filled in here. They run cooling tubes and heater lines to heat the mold up, inject the plastic, and we get that part out fast. So ABS intentionally shrinks. It's a really useful material. That and nylon. Nylon also shrinks, but not nearly like ABS. But nylon can do some things ABS does, like take abuse. I use my kids as testers. That's why I keep handing you parts, because you know what? I've seen them literally break a small handle. So, The fact that ABS is durable, man, I'm like, oh, I wish I could have carved this stuff. So, so it shrinks. So here's your problem. You're trying to print with a material that was never engineered for 3D printing, but it's just real darn useful. So as you try to print, you have a heat difference here. So let's say you're at 120 C here. Your head here is running at 240, which is actually the wrong temperature. I'll get into that next. Your environment is 45 C, and your humidity is less than 35%. Oh my gosh, she's talking all these parameters. You have to isolate if you're going to find your problem. Okay? That's what you're going to find out. That the reason I run these up to 45 C, even on a small printer my kids play with, is that I have less difference. When this head is coming out, that first layer is great. It bonds, does its thing. You know, everyone hates the first bonding. Believe it or not, that's not the biggest problem. The biggest problem is the temperature difference between the 240 C and the 45 C for material made to shrink. The larger the part goes, the more forces you have across it. So, if you heat your box to about 45 C, your stepper motors won't die. They're close. Your filament won't turn to goo running down. It'll be close. Literally, you'll be measuring, you'll be taking your little black marker and marking it and checking the temperature as it runs. Give it about an hour and see where you're at. That's usually when it stabilizes. Usually there for 30 minutes, you walk away and come back and forth. So it's about an hour until it actually stabilizes. This will solve most of your print problems to about 150 millimeters. Great. If your printer's not much bigger, most printers are 150, 200 millimeters. No problem. What if it's larger? Yeah, that's the problem. We always want big parts, right? It's a simple solution. The rest pretty much is the same, except for your environment needs to go to 85 C. So your motors are dead. Your plastic is parts have melted. And basically it's just a big pile of goo. Your fans will come off the bearings. So you have two choices. And I have my preferred choice. It's up to you. I used to love water cooling. And there's a, you can see that print head there. It's a water cooled print head we used to make and print all kinds of stuff with. I don't even do that anymore. I don't like pulling. There's so many nice tools. Like you can buy these pre-made reservoirs with pumps. You can buy the pieces that bolt on, run a couple of wires out. A couple $100, you can water cool your unit. Okay, stick one on your motor, one on the front of your print head. Get that temperature down. You're good to go. It'll reduce your lag, reduce your strings, reduce all that. And at 85 C, you got two choices. That is to water cool, or you make a ceiling with a movable hole. So I've known Joe for a while, so I'm going to ask him, how do you make a ceiling with a movable hole? I love those words. I've known Joe for years, so I have to pick on him. So my solution without having to deal with the water cooling is I use machine bellows. So here's the, if you look underneath the machine, there's guides along the side. There are bellows. We'll go over to a moving frame. And bellows that go this way with heat guards around it. And if you look at it from the side, the only thing that sticks down is the hot end and just the very hot end. Everything above here is exposed to atmosphere, and it has rows of heat sinks and forced air cooling. That guy stays about 30 C. I don't have to worry about filament jamming. I don't have to worry about anything in doing. The environment, if you look from the sides, I also have bellows on the sides with a glass door on the front and the back because I just like looking. Because I haven't got past that yet. I even got a little camera up here. I'm still looking. That's me. So it allows me in this larger machine, so that's the top, I now can go 85C all day long. I change the print heads over to metal, all metal, and I use steel nozzles, not brass. And now I can play with ABS, nylon, ABS with carbon fiber, nylon with carbon fiber, anything I'm looking to do. So it's literally just a parts machine. And that gets it 65% of the way to what I want. I can print 2-foot long pieces without any workage. I can run dual heads, so I can use some support medium. What I usually use is hips for ABS or nylon. You can actually run nylon against it and then break it apart. Hips is horrible. So some of the software I use actually prints ABS supports and then just adds a very thin layer to hips. Saves money, makes it easier. Easy enough. If anyone needs things printed, don't hesitate. I'm more than happy to share the printer wherever you're needing to do what you need to do. So if you want larger than that, you're stuck at 45C. So what do you do? Oh, also another problem. When you print mechanical parts, how do you get them to look and fit right? Here's another junk part. It's one of my regions. This little heating table, a hot plate for evaporating semiconductors. Total garbage. So how do you get the print? Your print can only be within your layer thickness up and down. And everyone tries to print the nice 3 round pieces for your bearing inserts and otherwise. I want my bearing inserts. When I take the part on the machine, I turn around, take the bearing, and go and press it in. So how do I get that to work? First, every machine has a problem. Okay. First, has everyone got to the temperature and materials and the environment and all that? You need to identify your problem. Okay? First and foremost. So, need a little notes here. I need a part. And that part must have bearings that insert here, and I've got something, a rod perpendicular to it. I'm going to print another machine. Which one do I want right? Do I want it dimensionally correct this way? Do I want it dimensionally correct this way or this way?
Yes.
I can pick 2. And why? And that's easy. When you're printing and it's not liquid, it drags. So if I take it, tell it to make a curve, it actually inside cuts the curve as it moves. So if I get it to pick 2 dimensions that's stable, I will take and I will design my part exactly the way I want it. I will copy it to a new layer, and then I calibrate the machine for its drag. How far, when it makes what angle of a turn. So I'll print small ones, large ones, right angles. And I actually get a caliper and I measure the drag. So I go to my original model, I copy it, and then I will figure out the drag, and then I will subtract off the drag for that size of dimension. I'll use an offset function or something like that. Now, once the drag works to drag the plastic back into the hole I didn't want it to have, I can take my bearing and press fit it, and I can even compute the pressure on the wall that I want that bearing to fit into dimensions. Simple trick, right? Works like a charm. With everything else, if you're dealing with ABS, and you've not dealt with the dented tin of, actually that's how I get it delivered. For some reason, I get 10 of these things, they're always dented. ABS cement, clear or black?
I've heard of that.
It is awesome. It will actually tear the layers apart, tear the part, and chunk it apart before it comes loose. It takes a few seconds to bond it, so I will build notches or guides, build my dimensions for my parts. I'll make little notches for it to fit together. I will even offset. So if I have a part running this way and this way, I know the drag when that part's made. I'll subtract off the drag. I'll take and glue the part, because the dimension I have for the glue, how thick it goes in after force. I just calibrate it a couple times, make your print calibrations, don't be afraid of it. Measure the difference. They align with the notches, they fit together. I can hit better than 50 micron accurate. And I can press fit all my parts now. I'm done. I could either spend my life trying to print the perfect part, but this process is hokey. It doesn't actually melt. It drags, it oozes, I mean, it's amazing it even works. Think about it. You're taking something even a liquid and dragging it across and figure, hey, it's got to be exact, right? I went here and here, it's not like that thing went like that to me. You also have a maximum sharpness, and it's really good to go ahead and plan for it. You can get sharp edges only at the bottom. You can get dimensional stability. One of those parts I had him try to break, you can try to look at it, even use, if you use the part where you're trying to print curvatures, print a sphere as a whole sphere, right? Everyone's trying to do this. If you try to print a sphere, try it. It's a nightmare. You have the smallest touch point possible. You have undercuts underneath this. So all your parts are trying to overhang, or this medium is trying to go up, and you get into the cutoff. So you end up with this ugly part. So a lot of times I will plan for this in the design. It's annoying the first time you do it. You spend a weekend just printing these little test parts and calibrating it. But then you're done. That's awesome. Because everyone has the tool. SolidWorks, SCAD he's learning, ETL, huh? CATIA. I have my favorite. I'm in parametric modeling, so I do organic structures. So none of those tools work for me. So I go Rhino3D and I use Grasshopper. So if you never use it, it's like a combination of CAD, drawing, and programming. And I can actually set up genetic algorithms to iterate to do the design for me. So stuff would take me a year to do, I can do it in a couple of days. So that's my tool. Everyone's got their own. But calibrate it, build it in. So what I do is I have a script that I wrote on everyone's programmer, somewhere. But then that's, go ahead and subtract it, or build it into your design. And you're thinking about how you're building it, go, well, that's this, it's 10 millimeters, I'm gonna go 10.15 millimeters. Oh, don't get depressed when you look at the drag. The first time you calibrate your drag and you look at this thing and you go, this thing's a pile of junk, I can't use it. And yes, you can. It is a wonderful tool. It has real world issues with it, but it does a lot. So calibrate your drag. I think my kids drag on just parts up to so big. They are big about making. Not getting gears. My kids make these. Actually, made a machine who mastered it, which is kind of fun. So I brought some of their molds. So does all that make sense? Everything I said. Is there any questions anyone else has? Any of the problems that you're experiencing?
As far as the calibration, I did mine a little different. I'm curious. I'm interested in what I did was I just put like most of my issues are my holes. So I just printed some of my more common holes, like 10 millimeters, 20 millimeters, printed it, measured the variance, and then I put some other things in the system. Is that the same thing?
That's the thing. The caliper, if you don't have a caliper, go buy one. Buy a good one, go buy one of the little holes that you won't even know what you're getting. Worst thing to do is have a bad caliper trying to measure and calibrate this. Because also when you calibrate, you're going to find out that your printer doesn't have round holes. This way is one, that's another, that's another. You'll be looking at it like, it looks round. So don't be afraid of it. Measure it and average all the dimensions. Do at least 3 different directions, not 2, not 1. And average around. So yeah, same thing. I just average everything out to try to make it close. And then I can compute how much compression I want on that variable part. So that gives me less. But this Oakley ABS, seriously, take 2 pieces of ABS, lay them like this. Yeah, let's try them. Is that what's on this book?
It's black magic for you.
Here, let's try this. All right, so it is absolutely surprising. Yeah, we're going to put glue in it for somebody. Isn't that awesome? No, I don't just thinking that's it's just great. So they will tell you that you need to go fast. Fast is a good word. So I don't even have any guides. I don't have any grips. Nothing. So I always test fit the parts and make sure they actually fit nicely together before I do this. So count to let's say 15, right? Or less. In an hour, you will rip this thing apart to get that out.
You just put the ABS glue on it?
I just stuck some glue on it, stuck it together. I think this is one of the badly printed parts. I guarantee you it's going to give, just slip it loose on my finger.
Does it leave any kind of residual?
Acetone will mess up your ABS big time. Here for a second. But literally, a lot of times I'll just take the part.
So I'm asking, will it leave like acetone or will it leave like residual?
Yeah, that's why I always plan for how much I need in a little test part. Sometimes you get used to the number, like you can see the little that's up there. Who's less and fix it out there, get it off faster than I just did.
What does ABS do to the, or acetone do to the ABS?
It's a solvent.
Yeah, I realize that.
So it literally gets between the molecules and lets them slide and move around. It actually affects, so ABS, you have the three main components, right? Acrylics, you have the butadiene, the rubber, and then you have the styrene. So that styrene really hates the acetone. If you ever throw styrofoam cup in gasoline, you get the idea. So it kind of like the whole thing on the end, it goes, ah, and it just moves into a glass transition. But
One of these I've done from all planes is I made an ABS part and we poured around fiberglass on the outside, just painted some acetone on it and then tubes.
oh yeah,
Would that glue do the same thing?
yeah, but it actually will fill in all the little gaps, and it's more consistent.
Okay.
So a lot of times I'm wanting exact parts.
Right.
So I know how thick that ABS, once I give it a good squeeze, is on average for the surface area. I usually put little notches. I'm done. And then when I go to put my bearing in, I'm within 50 micron in the Z direction. And so I can plan that out. Yes.
So you're putting ABS on a glass plate,
Uh,
and you clean it with acetone a little too long?
I'm not a big fan of the glass plates. I'm a big fan of the glass plate with something on it. Yeah,
And
and
if you put ABS glue on any kind of a hard surface,
yeah, but it doesn't make that electrostatic bond like it will on the PEI or the Garolite. And that's what you're really looking for. It's kind of more of it's bonding to the glue has a surface area, and then it's usually, the bond strength is really low because you're dealing with just almost the air pressure and a little covalence between them. And it's nothing like the grip you're going to get from PEI against that ABS or the Garolite. Because you just get the mechanical response with those surfaces.
So did you say you sanded the PEI to get a surface on that?
Yep.
What grit?
60 usually.
60.
Yeah, I know. Everyone says, you need 120 grit or whatever. No, I like 60. I want the grip. Most of these parts, I mean, that's off of a 60 grit print. You have to renew it every so often. You'll know. Every 10, 15 prints, you just sit there, you keep a little nearby, you do a little extra on it, and then you'll clean it and off you go. If you're printing small parts, 75 or less, no, try the Garolite. It is awesome because you just don't deal with the issues. I mean, you just run print, pop it off, run print, pop it off. So.
so do you make house calls?
I will be happy to help anybody anytime because I'm still learning still. I'm always trying new techniques, different types of printers. I'm interested in the microfabrication, build a lot of microfab stuff. So I actually have micro printer that I print 1 micron accurate parts from. So not for everybody. But so you want to make, who was wanting to make a bunch of parts? You? Who was wanting to? Joe. Master mold, master mold. Make a master print of what you want. Cast urethane, cast whatever you want into it. Who wants metal parts? Ah, there's people there. And I saw that hand. And hand, okay. So, I've got some really great news and some horrible bad news. There's several ways you can do printing in metal. The easiest, I don't know where all that white's coming from. The easiest is doing a lost polymer process. Okay. Anyone done lost polymer? If not, you're good. Did you use the right grade aluminum?
Definitely not.
Hmm?
Definitely not.
Okay. A lot of people buy 6061 and it's not made for casting. There's a great guy on eBay, makes these off of old heads. Find them. It's easy to find them.
What about 3003?
You're still talking about an extrusion?
No, well,
Is it an
no,
extrusion?
it's just sheet good.
Is it machine good?
But sheet goods like
Oh yeah, those
full
are
white sheets that are pressed out or whatever.
they're extruded.
Right?
Yeah, they actually extrude them out. So what happens is when you go to cast them, they take higher pressure. So you'll pour it and you'll get that problem at the bottom. Every problem is in that little cube. And even though it's 3D metal, it is all there. So you can do either a lost polymer, you print a PLA part, and then this will look a lot like a gear, etc. It's got some extra teeth. This is off of one. This got made. Yeah, we. Second is, you want to fix that. Find a castable aluminum. Spend the money. Otherwise, it will harden, it won't flow. You'll have to use pressure or spinning it. And trust me, there's nothing worse than spinning molten metal and something going wrong. Concrete explodes if it hits it. Okay? The other problem is aluminum, which is really horrific. As soon as you start to pour it, oxidizes. So, you can take and run stainless steel tubing out of your mold down, take argon, blow down through your mold, clean your PLA out. That cube actually shows where there's ash that cast into it. Was left over. You bubble argon up through it. It'll take your hydrogen out of your aluminum, scrape off your slag, and take your little cover and just blow the aluminum into your mold, and it'll fill from the bottom up. You'll have this beautiful part. You can actually pull out really fine details. You'll be able to see the ridges. Real simple process. The 15th or 20th time you finally get it back. So there's another one. Two of those. You can make a little extruder. You saw that. You can extrude out the metal with a binder. So you got like bronze or stainless steel powder. That's really great. Except you can't use aluminum. That's a big setup because the aluminum powder you may buy is already oxidized. So you got aluminum oxide and trying to bond it together, you're basically getting this really good cookie. And it takes the right setup. You have to bring this thing up, 900 C thereabouts to really get it set up and get the temperature faced. And then you're dealing with the problem of, oh my gosh, oxygen got to it, it oxidized. You can use a standard kiln, nothing fancy. Let's see here. Joe always makes stuff, so I have some good guesses with Joe. Lost polymer. Another thing about these little Paragon kilns are great because they're cheap, relatively. Computer program, you can heat them up, burn it out. Your PLA burns off about 3 70, 80, thereabouts. And then you can just put the whole thing back. And then you run your temperature up, melt your center, your bronze or other mixture. Bronze is a great choice because it doesn't oxidize in air as bad. You can get away with a lot of bronze and brass. Stainless steel sounds like a really great option, except this is the perfect material if you have a laser. Outside of its expense. By the time you get enough of this stuff to go on a machine that's big enough for a powder bed, you've already spent $4,000 to $5,000 before you even touch your laser. If you try to do a cast of this stuff, you cannot do it with a standard kiln. You really have to have something to go hot enough, maybe about 1200 C. Those machines are going to cap out around 1100 C. So I wish those work in those little cheap kilns. You'd have them all over the place. There is another option, which is a lot simpler than doing the lost polymer process. And that is you can print your PLA shell, whatever little, say you want to make a small bracket. Print it, take your part, subtract it out of the surface. You're going to figure out how to do shrinkage, you have to do calibration on it. But get bronze clay or brass clay. You may not have ever heard of this. You take it and you press it into your mold, your PLA mold, whatever complexity you want, and then you just burn it straight. You put it in some charcoal fibers, some old wood charcoal fibers to take up the oxygen, so you won't need something fancy. Put it in there, the PLA burns off at 380, you give it a little while, you bring your temperature up, bring it back down, you have a centered metal part that you print. Now you can't go super complex or super big because metals are horrific with their own right. I can take a piece of piano wire, I can take a torch to it, I can then wrap it around my finger like it's clay, I can heat it up, drop it in water, and now it'll break like glass. So metals have their own characteristics, way beyond the scope of this. But bronze is really cool. But it's a great, there's actually a machine that somebody's coming out, they do that, they just print the PLA shell, automatically fill it. They have this binder that it'll shrink at a certain rate, they plan on it. I'm still kind of curious, I can't understand how they're not getting the breakage, because if I get a center shaft and that's shrinking, this has to crack. I've not seen any parts they've made so far that actually has a center shaft. I've been looking, like, how do they do that? Trying to steal it. So, there's polymer if anyone wanted to do liquid, laser, anything like that. You know, talking about those machines. So, I'll get down here. There's different types of printers. Absolutely. They all have the same, similar orientation, regardless of what you're doing. How many know what microscribe is? Two-photon process. So, this is about 60 microns big in full 3D. It's a two-photon process. And it is going to be the future eventually. Not for some years, but the machine's already out and is purchasable if you have the money. They take an excimer laser, they fire it down in infrared 700, 800 nanometer range. And it's an excimer that puts so many photons that two photons hit the same molecule at the same time. It looks like half the frequency, and it polymerizes. And they can move this tiny dot in 3 dimensions inside that vat wherever you want at high speed. If you've never seen it, it is the machine you're dreaming about. So you will want that. One other topic, your down tubes. A lot of you have these. A lot of machines will come just with the standard down tube. Throw away. Use these Teflon tubes. They'll cost you a couple of bucks to master plus shipping. And they will guide your tube a lot easier and you can see the part. So if you get a jam or a break, you can see it. The other thing is that these larger diameters will play a neat little trick that I once found. You may get a filament that breaks, or as you're unloading or loading, but they get wedged inside here and the other film will go by. Yeah, then you're just gonna like, why is it failing? Everything's right. So you ever see that? This stuff is perfect. It's the right diameter. It's really close. You never have to deal with it again. It's just a couple of bucks. It's well worth it. Any questions? Yes.
Oh, is that, on measuring the foam?
Yeah.
Okay, so you take two axes, 5 feet, every foot or so, average, right?
Right.
Now, if your filament's 10% over, you're 21% more plastic going through.
Well, I'll measure it by the volume.
Right, what if your nozzle is actually smaller than what's advertised?
Well, see, the problem with nozzles, so I designed a 3D printer in 2007 to print full three-dimensional parts, 25 micron accurate, full color. And I actually got the process to work. So why am I not seeing it? There's this horrible thing that happens when you get in small scale. And you take a nozzle and you get down, and it's 400 micron on average. There's a reason a lot of the common printers are 400 microns. 200 microns, you think it'd be twice the pressure. You're getting into the world of the micro, and at the micro level, electrostatics rule the day. Explain. Whale has no idea what surface tension is. A water spider lives by it. Everything changes by scale. So as soon as you drop below that half a millimeter scale, electrostatics start ruling. You go from a 400 millimeter nozzle to a 200 millimeter nozzle, you're going to be greater than 8 times the pressure. Because, and if you go even smaller, it's exponential. You can actually take water or even a polymer that flows like water, shrink the nozzle 50%, and it'll act like it's a concrete stop. So that's why we're limited to certain scales of these prints. But it fits. About 100 micron to a couple of meters. Yeah, it's a great overlapping technology. It's cheap, it's easy. If you measure your parameters, get your environment variable set, you can go along with it. You have a question?
There was that, Teflon tubing, I haven't seen one that clear before. That's white and
It's like this, so you put it down the master has. So you can look it up at the right ID, the OD, it's off just fine here, just enough to get it from the window.
It's clear, most of the,
It's thin enough to see.
yeah.
If anyone ever wants to learn about how to build a liquid printer, believe it or not, that's the magic, is this little Teflon sheet. Then you can use a DLP printer, pocket laser, whatever you want, to build you a laser printer with barbecue machine. So if anyone ever interested in that, we're happy to take it down that.
We could have it as
Think
a
about the one
feature.
to do the like LCD. I guess it's more like the
LCD, yeah.
LCD material.
So what it is just this UV resin. And what they do is they count a little bit of ultraviolet. On the bottom, that has a little frame that holds this tight. And then what they do is the vat sits here, your piece goes down, sits on it. They project the pattern. It hardens because as the light goes through this material, it disperses. The closer you are, the better it is. So it's higher intensity and breaks off. So it's just enough to cause that polymer, and you have to wait on the amount of time. You really want UV, but like laser drawing with galvos. But it's the same thing, and then you lift it off. Now there's some that actually have an oxygen membrane that is just really awesome. But that's a little bit more tricky. When you can order this from McMaster for a few bucks, put it in a little metal frame, put you a mirror, DLP projector, and one axis to move it up and down. You now have a lithography machine. It's not, none of this is rocket science. It's invented by people who just figuring it out just like we do. They just got a few more years. Moisture. One last note. If you do not have some of this, go find it. You stick it in the oven and you recharge it, it turns blue. Drop it in your filament. Do not leave your filament out in the open. Keep it under 35 degree or 35% humidity. And change this. Because the moisture will go through your seal. I don't care if it's pepper or whatever. A lot of times I'll put rubber sealant around the top. If I've got a 15 or 20 pound roll, I'll spend a couple of $100 on that thing. I don't want to take it out and wait and risk sticking it in the oven for 4 hours. I want to just use it. The other problem you're going to have is if you leave the roll on your printer exposed to the environment, it's going to go bad. The little roller I gave you is one that my kids left out. The first one we printed. The second roller with all those little notches is where it's sat out for 3 hours. Yeah, 3 hours. See, you got a print that runs 40 hours. And a lot of times I'll keep machines. I keep all my printers actually in a room with a dehumidifier set at 35%. That's how I get pretty prints from the beginning to end, and I don't have to worry about it. But keep your filament up. Not everyone's going to have a room they're going to dedicate to this. Keep it dry. Keep this charged. Change it once a week. If it turns pink, you just lost your filament for a day, unless you go back.
What temperature are you looking at?
It depends on the instructions, about 110 Celsius. Oh, the filament? It depends on the material. So talk to your manufacturer, they'll have a spec. So I'm a big fan of that. There's a couple of USA manufacturers that I trust, Knox3dp and a couple others. They've never let me down. I buy 20-pound spools from them. And I've never had a bad print from them. I've had bad mistakes, I think. I've not had bad material from them. So you're not giving it a whole lot of time. Jam break it after it. It's got it needs about an hour. You can see what it's doing. It actually bonds into the ABS. Any other questions? If anyone wants any of this for the glass beds, when you're printing ABS, this will make your life much better. You're more than welcome to it. You want it? A little bit of water, spray some water, a little bit of soap, and then you just slide it around where you want.
Thank you.
If anyone needs any big engineered parts, we're happy to help you out. I'm not going to spend the crazy time I have trying to get that stuff to work on the printer. If you want to do 1,000 units or so, or these rubber molds, we're more than happy to show you how to do master molds. You can work your way up from prototype, pre-production, and then into production and your home. Anything else? Great talk. Thanks, Bruce.